Hey everybody, I like to start the year with exploration 1.1, instantaneous rate of change of a function. I like this lesson because it allows us to look at a problem situation. I like this problem because we look at notation. I like this problem because there's some calculator keystrokes you might learn for the first time. I like this problem because it really connects to a big part of what we studied this year, and that is instantaneous rate of change. All right, our problem situation is right here. The diagram shows a door with an automatic closer. I don't see the closer, but I do see the door here. At time equals 0 seconds, someone pushes the door. So let's say that this door had originally been closed, so this line segment would have been flush with or horizontal with the two walls. We'll call these walls. And look at you, you're so cute. So let's imagine the door was closed, and then you've got this great big force. Look at your big hand. You push that door open. Now, I don't know how far this door has gone, and it's very possible that this door could have gone 180 degrees over here, hit the wall before the door closer, the automatic closer, requires it to come backwards. We don't know that because we don't have the full picture, but we can kind of think through it. Okay, the door, it swings open. It slows down, stops, starts closing, and then at 7 seconds, it slams shut. So we know that 7 seconds is the total time that this door has gone open before it returns closed. As the door is in motion, the number of degrees, lowercase d, it is from its closed position depends upon time, lowercase t. So, and a good thing to do to get into a problem is kind of think about the independent and dependent quantities, and the variables that represent those, and then also the units that represent those quantities. So I think it's always a good idea to kind of slow down in a problem and think, okay, ask yourself this series of questions. What's the independent quantity? Well, that's time. What's the variable for that independent quantity? That's t, and how is t measured? And that's in seconds. Likewise, I do the same kind of questioning in my brain is about what is the dependent quantity? Well, that's the door as it opens or closes. That's the context of the problem. What's the variable that represents that situation? That'd be lowercase d. And what are the units of that opening and closing door? That'd be degrees. Alrighty, now before I continue, let me just say this. I hope that you've already attempted this worksheet, and even if you only answered 1 or 2 questions, that's okay. I'd rather you attempt it and get stuck, and then me come back and we can kind of finish it together. I think there's more good learning that takes place there. All right, number 1 says, sketch a reasonable graph of D versus T. Well, time is positive. It looks like it goes from 0 to 7 seconds, and that's going to be graphed along the independent axis. And then the degrees, which is the dependent quantity, would be the vertical axis. So I'm going to put D as a function of time here and time here. So D of T is measured in degrees, and T is measured in seconds. At t equals 0 right here, I know that that door was shut, so it wasn't open any degrees. So that's 0. I also know that, somewhere over here, we'll call that 7. At 7 seconds, the door is shut again. It's closed. So the degrees that it is open from its closed position, whatever, is 0 as well. So I have to have some kind of graph in between these two t-intercepts here. This is 0 and this is 7. So let me go back to the problem. It says at t equals 0 seconds, someone pushes the door. So I'm thinking as someone pushes it, that door's opening pretty quickly. So I would say that the degrees are increasing pretty rapidly. At some point, that door is going to stop opening and the degrees are going to top off, and then the door starts to shut, which means the degrees are getting less and less, getting closer to 0. For me, I'm thinking, that graph is probably something like goes quickly, it stops opening, and then the degrees start to slow down, and then all of a sudden it says it slams shut. I'm thinking it should be the graph of this This function should be pretty steep right here. Anything of this kind of nature, whether you have the graph swing outward like this and down, anything like that would be acceptable. There's no wrong answer. It's all a great representation of that problem situation. All right, so let's look at number 2. Suppose that D is given by this equation. D equals 200 times T times the exponential factor 2 raised to the negative T. Plot this graph on your grapher. Sketch the results here. So now what we're going to do is we're going to kind of test and see, compare how our sketch compares to this equation that could represent this problem situation. So grab your calculator, whether you have your own or you've downloaded one. Okay, go to your y equals and go ahead and enter in 200t times 2 raised to the negative t. Of course, we're going to have to use x, so x is now our new t. I would encourage you to put the multiplication dot here just for the operations itself and how the calculator reads it. If you immediately press graph, you're probably in a standard viewing window. We don't need all 4 quadrants. Our problem situation is really contained within quadrant 1, so I would suggest before you do anything else, think about the reasonableness of this graph and maybe where it's located. Go to Window. Remember, the x's now represent the t values. My x-min is 0 and my x-max is 7 seconds. How do you want to count from 0 to 7? By ones? That's fine. If you don't want to have any of those little blocks that represent each of the spaces between 0 and 7, you can change that 1 to 0. All right, well, what's our y values? Now, our y is going to be our new d value. So let's think about that problem situation. What's the minimum degrees for that door to be open? Well, that's 0. Now, y max? Well, I don't know what's happening here. Could that door go to 180 degrees? Sure, I guess it could. So let me just go ahead and estimate and put 180. Now, I don't want to count from 0 to 180 by a scale of 1. So I don't know, probably change it to 10 or 20. So the x-res, we'll leave that for statistics. We're good right now. So let's go ahead and press graph. Now, do we have to worry about our mode being in radian or degrees? No, we don't have to worry about that. Okay, because we're not working with degrees, basically. We're just working with values right now. Each of these values up along the independent or the dependent axis represent a degree value. So we're okay. We don't have to worry about that. It won't matter what mode you're in, radians or degrees. Well, now compare this graph that's been modeled by this equation to what we had. And you know what? I'm willing to accept this sketch that I made as saying, I think it's reasonable, looks fine to me. Okay, so let's plot this graph. Looks like it opened pretty quickly. It stopped. It's slowing down. And then I don't think this graph accurately reflects that the door slammed shut, but I'll just work with it. This is an equation that represents and models this problem situation. And let's make sure and label. All right, let's make a table of values of D for each second from t equals 0 through t equals 10. Now remember, this is kind of weird because the door slammed shut at 7 seconds. So I'm really curious to see what's going to happen after 7 down here. I know at 7 seconds I have 0 degrees. Oh, let me get the table up there. Sorry about that. So I'm really curious to see what's going to happen here, because all I care about, and I should label this as 7, and maybe label this as 180, because I think I did go up to 180, and I probably should do that along the dependent axis here too. Maybe have that, actually it's not going to matter up here, because if you think that it opened all the way 180 degrees, this could be 180 here. If you don't think that the door opened 180 degrees, well then, you know, this could be whatever you want it to be right here. So this really probably doesn't matter. And probably that doesn't either. All right, so going back to the table, pardon me, as I digress there for a minute. I know at time equals 0, my degrees are 0, and I know at time equals 7, my degrees are 0. So this equation is only going to be used for 0 to 7, so these numbers down here probably won't have any meaning to us. All right, how do you find these values? Well, you guys know you can go to your table. I'm not a big fan of the table, but you can go to your table and you can see all the values here and start recording them. So at 1 second, the door opens to 100 degrees. And then at 2 seconds, the door is open at 100 degrees. So I'm just estimating maybe this is here and here. We'll see more detail in just a minute. 75 degrees at 4 seconds. The door is closing because the degrees are decreasing. 5 seconds, 31.25. Let's see what 6 is. 18.75. Okay, I'm continuing my table. 7. So for this equation, 7 is 10 degrees. I probably better take that off because they wanted me to use that equation. However, in the problem situation, it told me that the door was shut, but remember, which I need to, that we're using an equation to model that, so that might not give us a true 0 there. All right, let's see what happens at 8. 6.25. So if this is the equation that we're using, oh, and look at this right here. I highlighted this because I want to use all the decimals. 3.515625. And then that one right there. So this equation, it's a good model for what's happening, but it's not an exact model because remember, the door would have been shut with 0 degrees from here on down. But that's okay. Sometimes that's the best we can do is just use models, equations, and then throw out all that extra data that's not that critical. Okay, so of course you're going to use the table. So let me go back and let's talk about another way to fill in these values. I want to talk about 2 ways. So I'm going to go back to the graph. If I hit trace and I type in 0 and enter, it's going to put me on the point on the graph that's determined by that equation. So I could just capture 0, 0. While I'm still in trace, hit 1. At 1 second, the door has opened 100 degrees, and that's what the table gave us. Now at 2 seconds, the door is now starting to close, but it's open 100 degrees. So this table suggests that somewhere between 1 second and 2 seconds, somewhere in between that time frame, that door swung open to its maximum and then started closing. We don't know exactly what it is. We can find it because we've got features on the calculator that allows us to do so. I'm still in trace. I hit 3, I hit 4, hit 5, etc. Now I hit 7 and then I hit 8. It's going to tell me error. The reason it tells you error is because your window setting is only to 7. So if you wanted these values by using the trace feature from 8, 9, and 10, you would have to go back to your window. Let me quit. I'd have to go back to my window and I would have to adjust my time maximum to 10. Because if I'm using the graph and the trace feature, okay, it gives me an error when I'm trying to get onto a point on the graph that's not displayed on the independent axis. So just kind of keep that in mind. That's one kind of downfall of using trace, is that you might have to go back and adjust your window. That's fine. All right, I wanted to show you another way to get these values. Okay, we have the equation that represents this problem situation stored into y1. You may not know this. Okay, I hope you do, but if you don't, watch what I'm going to do. I'm going to quit out of the function grapher here, y equals, so second mode. Now, hit the green key, alpha, and then hit trace. You get a pop-up menu that lists all the different y value, or the y equations that we have in our function grapher. Well, right now I have the equation stored in y1. Had I had it stored in y2, I would be accessing y2. But let me go back up to y1, press enter. So again, that was alpha trace, pop-up menu. Press enter. Now at this point, we want the calculator to do the computations for us to generate these values. So if you don't want to use table and if you don't want to use trace, you can call up the name of the function where you have the equation stored, and I would do parentheses. I would do 0, close my parentheses. So you're telling the calculator to plug in 0 into the equation, plug in 0 for x, into the equation that you have stored in y1. Yep, 0. So then I can use my up arrow, go back up, press enter. Now I have an editable line. Let's come here. Let's change that 0 to 1. Go back up. Over here, change it to 2. Here, change to 3. Hopefully you believe that you can get those same exact values by using this feature on the calculator. And this is going to come in handy for us many times this year. So again, alpha trace, pop-up menu, and then evaluate that function at your different input values. All right, look at 4. At time t equals 1 second, does the door appear to be opening or closing, and how do you tell? Well, I'm going back to the graph. I'm going to hit trace, and I'm going to hit 1 to remind myself. Now, where was that point? So what are we going to say here? Okay, in calculus, we try and respond to questions by taking the question and restating it and then filling in our answer. So I'm going to restate the question. And I'm going to abbreviate, and that's okay. I'm going to leave a blank here for you to think about what's going to go there. What word? How do you tell? Okay, that's going to be more your explanation, like explain your reasoning. So I'm going to put because. And then I'm just going to leave some blank space here. So at time equals 1 second, the door appears to be still opening. Think about what your response would be. I'm sure we can have a couple of different responses. If we were together, I would say let's brainstorm it and then record what we think is maybe a really good, better answer. The door appears to be opening because I would say, and someone might say, the degree seems to still be increasing. The graph is going up still. All those are great, but we want to be specific. So if the D values or the graph is going up still and increasing, I'm going to say because D of t is increasing. I'm going to put another blank here. Another way to say this, and you guys are probably comfortable with this, is you could probably say something like the slope of D of t is positive. Certainly the slope of the graph right here is positive. Now you're getting into calculus. When you start talking about slope, then you're really getting into calculus. So let me share some things with you. At this point, this would be an excellent explanation for why the door appears to be opening. So I'm going to do this little squiggle here. Just kind of squeeze some more content in here. What if you said because, and I can abbreviate, and it's certainly acceptable, because the slope, and I would put of what? Because when you just say slope, we don't know what slope is. The slope of the D of t graph is positive. Or you could put the symbols greater than 0. That's fine. So in calculus, if we were asked to justify this, our justification would have to be because the slope of D of t is positive. We're going to be spending a lot of time on that, but I just want to introduce that. Okay. So I wanted to kind of share with you some other notation as well. Okay, and don't worry about it. I'm just going to get it out there right now so you see it at least once. And the next time you see it, you'll be more comfortable with it. What would be notation that represents the slope of D of t? Well, what we use in calculus is we say the slope is d over dt, And then the slope of what? Well, what are we using to represent the dependent? We're using d. So d over dt is your way of saying we're talking about the slope of, and then right here, of what? Had this been f of x, we'd be putting f here. So we can actually rewrite this as the rate of change of d with respect to t. So what I'm going to do is I'm going to pull this d up top here and have dd over dt. And this notation right here represents the slope of d. So this is the slope of the function d, and it is greater than 0, or in other words, is positive. If that seems weird to you, don't worry about it. Believe me, we've got plenty of time to work on that. I always just kind of like to front load instructions sometimes and say, don't worry about it, because we're really going to dig in later. All right, let's look at number 5. Okay, so what is the average rate at which the door is moving for the time interval from time equals 1 to time equals 1.1 second? Well, I know here's where the door is at 1 second. Let me, and I'm still in trace, so let me just do 1.1 second. I bet I'm going to be very close to where I was before. Oh yeah, I didn't move much. I only moved like 2.6 and a little bit more change degrees. So I'm still increasing, it looks like, at that 1/10 of a second later than 1 second. So they're asking me, what is the average rate of change? So imagine this. So back over here on this graph, it's asking me if this is time equals 1 second and this is time equals 1.1 second, what's the slope between these 2 points that are on this graph? Looks to me like it's going to be positive because the d values are still increasing. But we have to find that value. What is the slope between time equals 1 and time equals 1.1 second? Well, let's set up a difference quotient. It's the change in the degree values divided by the change in t values. All right, what are the degree values? Well, it's the degree evaluated at 1.1 minus the degree that's evaluated at 1 second, all over 1.1 minus 1. The change in the degree values, and this is the notation that represent it, divided by the change in the 2 time values, which is just 0.1. It's good habit and good practice to always put the units in a difference quotient. So we know that with these numbers on top, these are degrees, these numbers in the denominator are seconds. All right, so let's go ahead and complete this and then let's go back and read the question to see if we've answered everything. All right, so the quickest way to do this is to go to the home screen. All right, let's set up a fraction bar. So alpha y equals numerator, denominator. Now we want to take 1.1 and plug it into our equation we have stored in y1. So alpha trace y1 1.1 minus y1 again evaluated at 1. Let's let the calculator do all that work and put it all in one place. Press enter. All right, let's record this decimal. All right, in calculus, we record to 5 places. We can either truncate or round to 5 places, but we should always have 5 numbers to the right of the decimal. So 0.336 and then 29, and that is rounded. And that's also truncated. Truncated means we don't have to worry about rounding. We just grab the first 5 numbers past the decimal, which means even if that 0 was a 7, I could still record what I have here and not bump up this 29 to 30. So in this class, we're going to round or truncate to 5 decimals, not 3, not 2, unless we're otherwise specifically told what to round to. Okay, just going to be common practice to go to 5 decimals rounded or truncated. Okay, and then we've got the units that fall in here really nicely. Okay, a comment about notation before I move on and look back at the question to make sure I answered everything. This notation, a change in D over a change in T, these little delta symbols, these little triangles, this is what you're used to from 8th grade or whenever you studied Algebra 1, maybe even before Algebra 1. This represents an average rate of change, an average rate of change. This up here, when we talk about the slope at an instant, okay, not through 2 points on the graph, this is instantaneous rate of change right here. That's what we were referring to, the slope at that 1 point at time equals 1. Well, that notation of an instantaneous rate of change can't be the same as the notation we use for an average rate of change. So this is really tied to an instantaneous rate of change, and this is tied to an average rate of change. This is change occurring at 1 point, whereas this is change occurring between 2 points. Back to our question. Based on your answer, does the door seem to be opening or closing at time equals 1? Explain. All right, so I'm going to say the door seems to be opening because so that's our answer. We can abbreviate. It's accepted on an AP exam because why? What is it about this number that tells us the door should be opening? What is it about the rate of change between these 2 points? Well, it's a positive number. And I would say because the average rate of change, delta D over delta T, is greater than 0. You could use the words is positive, but you just have to be comfortable with both. Symbols greater than or equal to 0 or greater than 0, or the words. So I think we've answered all parts to that question. Now let's move on. Number 6. Find an estimate of the instantaneous rate of change at which the door is moving at time equals 1 second. Show how you get your answer. Find an estimate of the instantaneous rate of change at which the door is moving at time equals 1 second. So coming back over here to your graph, okay, at time equals 1 second, the instantaneous rate of change is actually the change that's occurring at that one exact point. Well, we found an estimate of this instantaneous rate of change at time equals 1 by using a nearby time value to t equals 1. We used 1/10 of a second to the right of 1. This is actually an estimate of the instantaneous rate of change. And this question is just kind of begging us to know that. It's saying, you've already done it, let's do it again. So kind of what's common practice then to find another estimate? It's going to be similar to this, I'm sure. And it says, show how you get your answer. Show the work that leads to your answer. So we just want to use another set of ordered pairs. I would still use 1, but maybe now instead of using time equals 1.1, I might use time equals 0.9. So I would say that for me, I'm going to use, just kind of planning it out here, t equals 0.9 and t equals 1 second. Now, is there another set? Oh my God, there's an infinite number of time values you could use to estimate the instantaneous rate of change. It's acceptable even to use maybe t equals 0.9 and then t equals 1.1. That would be an acceptable, two acceptable t values, because doesn't 1 second fall between 0.9 and 1.1? Hey, another one, you could maybe use time equals 1 and time equals 1.01. That's only 1/100th of a second away from t. You choose which set of time values you want to use to estimate the instantaneous rate of change. And certainly, the closer you get to time equals 1, like this number, the better estimate you're going to have. These are still good estimates if you use these sets of time values, but this is probably going to be a better estimate. So I hope you guys all use something different, but I hope you all use the same notation down here. Change in degrees over change in time. I'm going to use this last set. I want to find the degrees that the door is open at time equals 1.01 second. Oops, subtract that from this degree of 100. And remember, extend that fraction bar. Go ahead and include your units. That way we don't leave anything to chance. I'm certainly showing how I'm getting my answer. Okay, look how nice and neat and organized we're being. Now, do you have to show any work here? Nope, not at all. Go to your calculator. I'm actually going to arrow up, arrow down. I'm going to come back and I'm going to edit the numerator and the denominator. So I'll make that 0. I'm going to insert a 1. Then I'll come down here, make that a 0, and insert, that's above the delete in blue, a 1. So let me just double check everything. It looks good. Press enter. Remember, we're going to record to 5 decimals, truncated or rounded, so that would be 20. So truncating and rounding would be the same thing here in degrees per second. So how does this number right here, this average rate of change, compare to the previous average rate of change? Well, this value is higher, but it's still positive. So does that suggest this positive rate of change? Does it still suggest that the door is opening? Yeah, it does. It's going pretty fast. So hopefully you learned some things through here. I mean, we revisited, talking about independent, dependent quantities, paying attention to what those quantities are, what their variables are, what their units are. We revisited making sure to set a window to view the context of the problem. We used an equation to represent the problem situation, to model it, but there's going to be some errors kind of with that equation. And those errors kind of occurred down here in the table where we knew these degree values couldn't be anything other than 0 because that door slammed shut at 7 seconds. It's still good equation to work with. Okay, over here we looked at some notation that represents instantaneous rate of change. Don't worry about that. We'll cover more of that later. We revisited average rate of change. We looked at notation on the calculator keystrokes that kind of, help us be efficient in these computations here. All right, we remembered that we probably should include the units in our work. Okay, we made sure to go back and always read the problem to make sure we're answering everything. Okay, we knew that an estimate of an instantaneous rate of change would have to be an average rate of change. So in this opening lesson, a lot has gotten out of here, come through all this, and I hope that you're okay. I hope you've enjoyed it.